Welcome. Today we are looking into realities of building enterprise AI systems on AWS. We are moving past isolated models into fully integrated architectures where AI inference cores interact seamlessly with data ingestion layers, serverless functions, and API gateways. There is a massive gap between the prototype illusion and production reality. In a notebook, you have a single user, static data, and you can ignore cloud cost and latency. In production, architects must deal with millions of requests, dynamic streaming data, exponential cloud cost, strict data privacy, and sub-second latency requirements. Our job is to bridge this gap through scalable, reliable architecture. With traditional ML, we are often built bottom up, starting with data. With LLMs, we must invert the design paradigm. We start at the top with the application, defining the user experience, latency limits, and business logic. This drives our LLM selection for evaluating trade offs between open source models, edge models, or commercial APIs, which in turn dictates our data privacy, chunking, and embedding strategies. To manage the complexity of ML systems, we utilize the FTI framework, boiling the architecture down to three logical layers: the feature pipeline, the training pipeline, and the inference pipeline. This strict separation enables independent inferences, allows distinct teams to own different parts of the lifecycle, and crucially, allows us to scale hardware independently based on the workload. Pillar 1 is the feature pipeline, which isolates data processing. We ingest raw data and pass it through a transformation engine for cleaning, chunking, and embedding generation, finally landing in the feature store. This centralized store is critical for preventing training serving skew. It guarantees that the exact same feature state is fed to both our training clusters and our real time inference pipelines. Pillar 2 is the training pipeline, which operationalizes our fine tuning. This pipeline consumes versioned instruct datasets from the feature store, processes them across our LLM fine tuning cluster, and deposits the output into a model registry. This treats the model as a first class citizen, storing and versioning weights to make deployment reproducible and rollbacks seamless. Pillar 3 is the inference pipeline, where we serve predictions at scale. The inference engine pulls real time vector DB access from the feature store and retrieves the appropriate model weights from the model registry. By ensuring strict version matching between models and features, we decouple the model logic from the data state and serve predictions reliably via a REST API. The greatest advantage of the FTI architecture is asynchronous scaling. The feature plane is CPU and RAM heavy and scales horizontally based on data ingestion volume. The training plane is GPU intensive, scaling vertically by adding specialized accelerators like A100s or H100s. Finally, the inference plane is latency optimized, scaling elastically, expanding and contracting based entirely on concurrent client requests. When deploying on AWS, you must choose where you sit on the AI infrastructure continuum. On the left, we have Amazon Bedrock for the out of the box serverless deployment. In the middle, Amazon SageMaker acts as our managed platform for ML. On the far right, for deep customization and research at massive scale, we rely on self-managed Kubernetes and VMs via Amazon EKS and EC2. Let's look at Amazon Bedrock, our buy option. It is a fully serverless black box offering maximum deployment speed for quick prototyping. You manage zero infrastructure and operate on a simple pay per API call pricing model. The core constraint here is limited customization. You are restricted to the models and configurations hosted by the provider. If you need to build, you use Amazon SageMaker. This is a fully managed platform that still exposes the underlying EC2 GPU nodes. It targets AI engineers who need complete control over fine tuning and custom ML logic. Pricing is pay as you go for active compute resources, meaning you must actively manage it to spin down idle instances to avoid cost overruns. This decision matrix summarizes the trade off. Bedrock offers rapid integration with zero operational overheads and per token pricing. SageMaker offers deep customization for custom enterprise LLMs with medium overheads and per instance pricing. Amazon EKS is for massive scale and cost efficiency, giving you absolute control, but it carries a very high operational overhead and complex auto scaling. For most enterprise applications, we implement retrieval augmented generation, or RAG for short. In the baseline architecture, a natural language query hits a retriever, which pulls context from a vector DB index. This combined context is passed to the generator, which is our LLM, which synthesizes a context aware output response. However, standard RAG has severe limitations because vector similarity search relies on word matching. It suffers from a lack of relational logic, missing explicit cause and effect relationships. This leads to fragmented information where crucial context is missed, and the generator passively accepts whatever the retriever outputs, even if it's contradictory. To solve this, we move to advanced RAG utilizing a knowledge graph. Graph RAG replaces simple vector proximity with a structured knowledge base. While it sacrifices some speed, it excels at answering complex queries that requires deep interconnected insights, giving us massive gains in contextual accuracy and nuanced synthesis. The next evolution is agentic RAG. Unlike naive RAG, which is straight through process, agentic RAG introduces an active reasoning layer. We provide the agent with a structured schema of tools such as search, APIs, databases, function calling. The agent creates an operational feedback loop, deciding when and how to invoke tools, evaluate data, and iterate before sending the final context to the LLM. We must acknowledge the financial reality of AI. Infrastructure costs are split across compute resources, cloud usage like idle instance time, data storage, egress fees, and real time inference costs. A poorly optimized AI infrastructure will turn an innovative project into an unsustainable money pit. Training can cost millions, and inefficient inference bleeds budget daily. To mitigate costs and latency, we implement intelligent load balancing across heterogeneous compute. We route high volume, simple queries to low cost CPU clusters. Complex GenAI requests are routed to high performance GPU or TPU instances, and data heavy requests are routed to nodes with high data locality to minimize network latencies during traffic spikes. Our core cost optimization layers focus on maximizing hardware efficiency. We use a hybrid instance mix, running mission critical workloads on reserved instances and batch processing on spot instances. For idle infrastructure, we use containerized request aware scaling on EKS to scale pods down to zero. Finally, we perform continuous benchmarking to find the optimal cost to performance ratio over time. Operationally, we must expand from MLOps to LLMOps. Traditional MLOps manages data versioning, weights, and compute orchestration. LLMOps wraps around this, adding governance for prompt template versioning, managing API schemas for function calling, enforcing safety policies such as toxicity, filtering, and continuous monitoring RAG evaluations for retrieval precision. This brings up to the complete enterprise AI blueprint. At layer 1, we have our foundation and LLMOps loop. Layer 2 is the AWS compute layer handling scaling and load balancing. Layer 3 is the feature store powering the FTI pipeline. And layer 4 is the logic node executing agentic RAG and interfacing with the application. Ultimately, we must treat AI not as a magical black box, but as a rigorous scaling engineering discipline.